Photoacoustic tomography has the goal to overcome that limit by using diffuse photons, photons that have been multiply scattered. So far, we demonstrated penetration up to about 7 centimeters. Multiple scattered photons decay much more slowly. The Wang decay constant is up to 10 millimeters. As a result, you can expect a limitation of up to 10 centimeters in scattered biological tissue. That's an orders of magnitude improvement over the conventional ballistic imaging. This movie here shows you how photons transition from the early ballistic regime into the later diffusive regime. Within a millimeter or so, you can count on ballistic photons, but beyond which, for practical purposes, you have too few to use to generate a sufficient signal-to-noise ratio. So we're going to overcome this diffusion limit and still provide you reasonably high spatial resolution, and actually when you're really shallow, you provide stunning type of resolution. Photoacoustic tomography is based on the physics of photoacoustics. As a physical phenomenon, this is a very old physics, in fact. Alexander Graham Bell reported photofilm over 100 years ago based on the concept of photoacoustics. He was the first one describing this phenomenon. His idea was to encode a sound signal in a light beam, propagate the light beam in space, convert light back into sound again. So what's going on here that's of interest to us is the photoacoustic effect. In the photoacoustic effect, light is first absorbed. It generates a temperature rise. Due to thermoelastic expansion, we produce acoustic emission. Bell was much more interested in audible frequency range. Nowadays, we're much more interested in the ultrasound frequency range. By increasing the frequency, shortening the acoustic wavelength, we achieve very high resolution, spatial resolution. So we're combining this very old physical phenomenon with a very modern imaging concept, tomography, to form a new imaging modality. Just remember that in Bell's days, tomography was not even in the lexicon. Let me start with the circular geometry photoacoustic CT. We start by broadening a laser beam, make sure we stay within the safety limit. Here we allow photons to scatter, unlike the ballistic imaging modalities, where we reject multiple scattered photons. Here we tolerate scattering. That's the only way to penetrate deep in scattered biological tissue. So here all photons are useful photons. When light is absorbed, it generates a pressure wave due to the photoacoustic effect. Every millidegree will give you roughly 800 pascals pressurized in soft tissue, which is quite detectable already. So that means if you generate hundreds of milledegrees, you will get a very good SNR to work with. This heating will generate acoustic emission. We place a number of ultrasound transducers outside the tissue to receive the photoacoustic waves from which we form an image. Because ultrasound scattering is orders of magnitude less scattering, or ultrasound scattering is orders of magnitude less than optical scattering in biological tissue, we can form a very sharp image by detecting the sound signal. However, the contrast mechanism comes from light absorption, so we're detecting the optical properties using sound. As a result, we have access to all the motivations I just talked about. You do have to deal with math. Let's assume you have a 3D unknown object. You essentially bathe the object with photons. You generate a volumetric photoacoustic sound source. You place a number of ultrasound detectors on the detection surface. For a given detector, at time t after the laser pulse, we're integrating the initial pressure rise on this spherical shell. That integration is called the spherical redound transform. Very much analogous to the linear redound transform used in X-ray CT, except here we're dealing with a two-dimensional integration on a curved surface. So this is a much harder problem to invert. If a readout never inverted this problem, our field had to deal with this problem. We found a universal back projection method that allows us to deal with three standard detection geometries: planar, cylindrical, and spherical detection. P is a function of detector position or not, versus time t is the signal we received. We have to properly time delay the signal from the detector back into the object. By including the high frequency component, by taking a derivative, we get an exact solution if we integrate all the detector signals by using this differential solid angle. This is a nice way to integrate all the different detection geometries. This initial pressure at first glance is a mechanical contrast. However, this pressure is directly proportional to the amount of optical energy deposited locally. As a result, we can measure the optical energy distribution, which is optical contrast instead. One point I want to make here is that unlike standard X-ray CT, where X-ray photons travel in a straight fashion, but here, photoacoustic waves travel in all different directions. The other difference from X-ray CT is the temporal resolution. In ultrasound detection, the speed of sound is slow enough for us to resolve in a temporal fashion, where X-ray travels at the speed of light, which is simply too fast to resolve temporally. So we have this extra dimension, time, in our favor in tomography. This slide shows the first set of functional photoacoustic images. We wiggled one side of the whiskers of a small animal. The contralateral side of the brain was hemodynamically activated. The color signal here shows the hemodynamic activation. The light actually wandered through the skin and skull, reached the brain cortex in order to excite the photoacoustic signals. This cannot be done using standard ballistic optical imaging modalities such as confocal or two-photon microscopy. So the demonstration of this capability for the first time showed the key advantages of photoacoustic tomography. As a result, our field was galvanized for exponential growth, as you can see from this chart. And plotting the number of papers presented in the largest conference on this topic as part of the Photonics West. Before 2003, this was one of the smallest conferences. After 2009, this conference became the largest in Photonics West, and is still growing. Next year's data is off the chart, in fact. So we wonder why this field is becoming so exciting. One of the key advantages of photoacoustic tomography is the multi-scale imaging capability in vivo with consistent contrast, because we always measure optical absorption. I'm plotting the penetration capability versus the spatial resolution. You can see here already that we are able to cover a wide range of biological structures, from organelles through cells, tissues, all the way to organs. This dashed line representing the depth to resolution ratio. No matter how deep you want to image, we can provide you roughly 200 pixels in the depth direction. So that means you always have a good image to work with. This imaging, multi-scale imaging capability is extremely important in biomedicine. In current practice, for organelles and cells, we use optical microscopy, so that means we're revealing optical contrast. For tissues and organs, we switch to non-optics. We use MRI, ultrasound CT, and what have you. So that means you're looking at non-optical contrast. There's a huge divide between the cells and tissues levels. Photoacoustic tomography allows us to bridge that gap and provide you a continuum so that we can correlate images easily acquired across the entire length scales that are important to biology and medicine. There are many potential applications. I'll enumerate a couple of them. One, to enable systems biology research at multiple length scales. Two, to accelerate translation of microscopic lab discoveries to macroscopic clinical practice. Each horizontal bar here represents an experimental system we have built in the lab. I'll go through some of them today. In the 2003 work, we used a single element transducer and scanned the transducer around the animal in order to acquire a 2D data set, which took more than 20 minutes. Now we have access to a 512 element ultrasound array that allows us to acquire the same data set within 2 seconds. So we're orders of magnitude faster now by using this parallel detection scheme. As I mentioned earlier, photoacoustic waves travel in all different directions. That means the configuration can be very versatile. For trunk imaging, for example, for a small animal, we can use side illumination. For brain imaging, we can use top illumination. However, the ultrasound array is fixed at the same position. This movie shows you a full-body small animal set of images. As we scan along the trunk, we acquire cross-sectional images of this small animal. This movie shows you the images acquired around the kidney region. And this is a still shot extracted out of this set of movie. We can focus on one region such as the colon area. As the colon becomes in focus, we can see the cross-section very, very well. Eventually the colon will get out of focus. This type of imaging capability is very important for drug discovery and basic science type of research in the lab. Again, the configuration can be very versatile. In photoacoustic tomography, we can switch to a linear geometry. We work with the Philips to modify this clinical ultrasound machine built by Philips for concurrent photoacoustic tomography. This is a linear handheld ultrasound probe. We flank the ultrasound probe with 2 optical fiber bundles for light delivery. With a single laser shot, we illuminate the tissue volume below this handheld probe for simultaneous imaging of a 2D plane. This array, this is an ultrasound array with typically 256 elements. All elements will receive the photoacoustic waves in parallel. That means a single laser shot will give you a 2D image, which is very fast. The data acquisition is finished within 100 microseconds. So that means motion artifacts can be minimized. You can see already we're targeting clinical applications. This is a patient bed. The system is located at the hospital at Washington University. This system works around this point, many centimeters penetration, hundreds of microns up to about 1 millimeter in spatial resolution. We demonstrated ex vivo the penetration of the system is about 7 centimeters. In vivo, this is the first case we imaged in a human patient. You can see features up to the depth of about 6 centimeters here. There's a breast tumor in another patient. You can see the breast tumor which co-registered with the ultrasound image quite well. Because we're using the same ultrasound probe to acquire both data for photoacoustic imaging and ultrasound imaging, the data are automatically co-registered. So we simply overlay these 2 images. The grayscale comes from the ultrasound, which has contrast in this case as well. But our initial clinical goal is not for breast cancer imaging. Instead, we want to stage the breast cancer. So the patient is known to have breast cancer, but we need to know whether there's any metastasis, whether the cancer has moved away from the primary site. The theory behind the staging is that all breast cancer metastasis goes through the sentinel lymph node, namely the first draining node away from the primary tumor. The standard procedure requires a surgery. We inject radionuclides, we inject organic dye. Those will flow toward the first draining node. Then the surgeon had to cut open the axilla area and follow the dye to dissect the sentinel lymph node for histology analysis. 90% of the patients turned out to be benign, but they had to find out through a surgery. We want to convert that surgery into a needle biopsy. We inject the dye only, which is clinically and FDA approved. The dye accumulated in the central lymph node becomes highly visible in photoacoustic tomography, so it's a very strong contrast agent. Once we identify the central lymph node, eventually we want to insert a needle. We can see the needle as well, so we can guide a needle biopsy, or in this case, we simply use fine needle aspiration to take cells out of the central lymph node. Then we do cytology to see if there's cancer cell inside the central lymph node. So once this is proven, we can improve this surgical procedure into a needle biopsy procedure. And so far, we simply place a little clip inside a sentinel lymph node after the patient goes through the standard clinical procedure. We radiograph it to identify the sentinel lymph node for corroboration of our data. Let me switch onto the microscopy domain, and there are actually two versions in that domain as well. I'll start with the acoustic resolution version. Unlike in photoacoustic CT, where we use a lot of unfocused ultrasound transducers, then we use a math to reconstruct the image. Here we're going to use physics to form an image. Let's assume there's an optically observing target in a piece of tissue. We illuminate the tissue with a laser pulse to generate a photoacoustic wave. Here we use a focused ultrasound transducer instead to receive the photoacoustic wave. You would get a time course like this. We can convert the time of arrival into depth because we know the speed of sound in soft tissue very accurately. This is essentially a one-dimensional image, which we call a scan. Then we can scan across the tissue to get a 2D B-scan image. If we raster scan on the tissue surface, you get a 3D image. Very much like photoacoustic CT, the time is important. That gives you the resolution, the depth direction. Because of the focused ultrasound detection, we get transverse resolution as well. So you have three-dimensional resolution by using this focused, time-resolved ultrasound detection. This photograph shows you the first 3D photoacoustic microscope. You start from a laser, route a beam through a fiber. The solid beam coming out of the fiber is converted into a hollow beam using this conical lens. This key component is shown here in this close-up. We focus the hollow beam into the tissue. On the tissue surface, we have this donut beam. We make the core of the beam dark intentionally to minimize the surface interference. The ultrasound focal point is co-located with the light illumination, so we can optimize the signal-to-noise ratio. Again, with a single laser shot, we get a 1D image in the depth direction. This head is raster scanned in this water tray to get a 3D image. You see a little membrane window right here, through which we pass light and sound. The tissue we want to image is placed below the membrane window. This system operates around this point. It penetrates about 3 millimeters. It gives you tens of microns resolution instead of hundreds of microns resolution. We can use this system to image humans. This area can be imaged very nicely. We can see all the blood vessels in the skin. This is a B-scan image showing you depth-resolved structures of the skin. We're imaging melanoma patients now. One of the important clinical procedures is to measure the Breslow's depth, the depth of the melanoma lesion, which currently requires cutting a piece of tissue out of the melanoma. Depending on where you cut, you may get different numbers as the Breslow's depth, which has quite a variability. The dermatology chief, Dr. Cornelius, we work with, wants to image the entire volume instead of just one cross-section, so you can have better diagnosis, better prognosis, as well as better therapeutic planning. Because of the much increased melanin concentration, which is a great absorber, we can image the volume of the melanoma quite well. Photoacoustic tomography images anything optically absorbing, including organic dyes, as I just demonstrated in the sentinel lymph node mapping. We can also image nanoparticles. This is a class of particles called gold nanocages. By tuning the size, we can tune the wavelength. This was tuned to about the near-infrared wavelength, so we can penetrate in tissue better. The bottom row shows a class of nanoparticles which are simply Beare nanoparticles. Because the tumor blood vessels are leakier than normal blood vessels, the nanocages are able to leak through the tumor region, and it gets stuck around the tumor. We can see them quite well. However, if you modify the surface of the nanocages for molecular imaging, we target MSH receptors of melanoma. those receptors are a hallmark of melanoma. The targeted version of nanocages will increase your signal by a factor of 3. So this is quite a bit of enhancement in signal-to-noise ratio. More importantly, we're much more specific. When we see the nanocages, we know we're seeing the melanoma because we're targeting the hallmark of melanoma. Another very interesting aspect of nanocages is that we're able to use the nanocages as a drug carrier as well. Because the cages are hollow, we can load the nanocages with drug. We can seal the pores at the corners of the nanocages using polymer. By heating up this region, we can shrink the polymer to open up the pores so the drug can be released into the targeted melanoma region. Then amazingly, when you actually let the nanocages cool off, the polymers will reseal the pores. That means you can come back and repeat your treatment. Of course, photoacoustics can be used to monitor the entire process, control the dose, and monitor post-therapeutic recovery. This is simultaneous imaging and therapy by using this important nanocage as a vehicle. We also miniaturized photoacoustic imaging probes for endoscopic applications. The key component is shown right here as a rotating mirror surface. We deliver the laser beam through this optical fiber. The beam is reflected by the mirror surface toward the tissue to generate photoacoustic wave. Some photoacoustic wave will come back and reach the same mirror surface and reflect it toward this ultrasound transducer. As we know, ultrasound transmission in tissue does not like air. This chamber must be liquid-filled to couple the ultrasound transmission. However, the motor we use does not like liquid, so this chamber is hermetic, air-filled. We separate these two chambers, but couple the torque using a pair of magnets. You can see the device in action right here. We image the rabbit esophagus as a demonstration of the capability. As we pull back the probe mechanically, you can get multiple B-scan images in real time. You can see the different structures due to blood absorption. One feature is that we can penetrate up to about 7 millimeters, in this case using the current design parameters. Using standard optic endoscopy, you can only penetrate up to about 1 millimeter, which is a severe limitation. That means you're going to miss all the lesions that are deeper than 1 millimeter. Currently, we're in the process of testing this device in humans for esophagus imaging. We can also acquire concurrent ultrasound images. So this is a dual modality imaging already by using the same ultrasound probe or ultrasound detector. We can also come back to the optical diffusion limit. So if we sacrifice the penetration, we only target a penetration of up to about 1 millimeter or so. Within this regime, we can optically focus light. So that means the transverse resolution can be determined by the ultrasound focal spot, while the axial resolution still comes from the ultrasound time of flight. The key component is here because we need to combine the optical axis, which is the vertical axis, and the acoustic axis, which is horizontal here. This is the ultrasound transducer. We need to make the two axes coaxial. This is a light-sound combiner, very much like an optical beam splitter. We have to make a device like this because it never existed. We use 2 prisms with a gap in between. We fill the gap with a liquid. The refractive indices between the liquid in the gap and the solid in the prism are highly matched. As a result, light can transmit very efficiently. However, the acoustic impedances between the liquid and the solid are highly mismatched. As a result, the photoacoustic wave reaching this surface or interface will be reflected through this ultrasound transducer. With a single laser shot, you can generate a 1D image. Then we simply raster scan to get a 3D image. This initial system demonstrated a penetration of about 1.2 millimeters, which is comparable to any other ballistic imaging modalities or better. This system operates around this point on this map. It gives you about 1 millimeter penetration, but gives you a single-digit micron resolution. We can use this device to image the tiniest of blood vessels in the skin. So this is a fantastic tool for monitoring of angiogenesis, as we know that's a hallmark of cancer. This is an extremely important problem in biomedicine. You can see here at multiple time points on the same animal, the vessel density increases and the vessel tortuosity increases as well. We can see both entirely non-invasively using endogenous contrast because blood is the contrast agent. This is a 3D rendering of the data set. Before this capability was available, my collaborator had to sacrifice a group of animals at different time points. He had to deal with very diverse variation among animals. Here we don't have that problem because we're monitoring the same animal over time. Again, just to show how well we can see blood vessels, this is a mouse ear we imaged. We can zoom into a smaller region just to get more details. You can see a number of capillary beds, a number of capillaries. The dots here are actually single red blood cells. So we're already at the single cell level. This is a 3D rendering of the data set. Some of us may know that there are two forms of hemoglobin, oxy and deoxyhemoglobin. They have different colors. That's why our arteries and veins look different in color. We can take advantage of that color difference. By tuning our laser wavelength, we can quantify the concentrations of both forms of hemoglobin, from which we can compute a very important physiological parameter called SO2, or oxygen saturation of hemoglobin. We can see here red represents arteries, green and blue represents veins. Many of us might have heard of pulse oximetry, but that only gives you a volumetric single number, only gives you arterial blood oxygen saturation, but not venous SO2. So it's very much limited. Here we're giving you vessel by vessel oximetry, and we can image both arteries and veins. This can be very useful in humans already. We demonstrate this in our own finger cuticles. You can see a bunch of capillary loops. These are hairpin-like capillary loops, unlike capillary loops elsewhere in the body, which are very much like the shape of our eye. So here we also imaged oxygen saturation of hemoglobin. We can zoom into a single capillary. You can see on one side of the loop, you can see very strong oxygen saturation. On the other side, it's much lower. That means the sharpest gradient is at the tip of the loop, which also means most of the oxygen is released at the tip of the capillary loop. This is a very interesting physiology. You can think of potentially many applications to study oxygen delivery in our body in the most fundamental way. Our neurology department is extremely interested in our technology. We all know that two-photon and confocal microscopy has been used very broadly in those areas. But they face very heavy problems because they have to remove the skin and also remove the skull, or at least thin the skull. By removing the skull, you release the brain pressure. That generates a lot of artifacts. So the hope is that you keep the full thickness of the skull. We actually started by keeping everything. So you can see this is actually the skin, but our naked eyes cannot see through the skin. We don't see any blood vessel structures in the brain cortex. Using our photoacoustic CT system, you can see all the blood vessels here quite well, in fact. How do we know they're true? We remove the skin, but we keep the skull intact, so we have the full thickness of the skull, in fact. The skull is translucent enough for us to see through. You can compare some of the bifurcation points here. They correlate extremely well. Just when you think you've imaged all the blood vessels, we brought in our optical resolution version. Now you can see a lot more blood vessels, which are deeper, so which would have been missed by using this entirely non-invasive modality. So this is somewhat invasive, but we can transmit through the entire thickness of the skull, where if you were to use confocal or two-photon, you can't get this kind of penetration. So this is a very big advantage in terms of neural imaging. We're working with our neurology department to study models on stroke, Alzheimer's disease. This is another demonstration of functional imaging. We can see here one side was lit up, the other side will light up. You can see here. So we're using electric 4-pulse stimulation to demonstrate this. This can potentially elicit some of the mechanisms behind the functional MRI bolt signal, where they have problem differentiating the contributions from both blood volume or oxygen saturation, because the bolt signal in functional MRI is sensitive to deoxyhemoglobin only. They're not sensitive to oxyhemoglobin, where we are sensitive to both. Just like any waves, photoacoustic waves have the Doppler effect. By using the Doppler effect, we can image blood flow. Once we have the blood flow information, we also add the hemodynamic information because we can image the blood concentration, we can image the oxygen saturation. We can also image cell diameter or vessel diameters. With all the endogenous parameters we image using the same system, we can compute a parameter called MRO2. That's the metabolic rate of oxygen, which is an extremely important parameter because, as we know, metabolism differentiates living tissue versus dead tissue. We demonstrated the importance of this parameter by imaging glioblastoma, which is the worst form of brain cancer. 1 week after inoculation of the tumor cells in the small animal, we can see a doubling of MRO2. So that means hypermetabolism has kicked in. That's why the cancer cells grow so fast. At the same time, we observed hyperoxia. So that means the oxygen saturation is very high. This is quite counterintuitive because normally when you consume more oxygen, you deplete oxygen from the bloodstream, which will result in a much lower oxygen saturation. In our case, it's the opposite. This is because hypermetabolism has stimulated a much increased blood flow, which overcompensates for the consumption of oxygen. As a result, you have hyperoxia. So that means the combination of hyperoxia and hypermetabolism may provide a mechanism for the earliest form of cancer detection, which requires non-invasive measurement, non-toxicity, because we don't inject any contrast agents. As you can imagine, for mass screening, if you inject any contrast agent, even a 0.1% complication rate multiplied by hundreds of million people, you will have a huge problem to deal with. So that's one of my dreams down the road, to test this in humans and see if we can provide an entirely non-invasive, non-toxic cancer screening tool. We're trying to push this vessel-based oximetry to the next fundamental level, single cell level. Can we image a single red blood cell and quantify its oxygen saturation as well? You can see this device scanning at 1 hertz, which is easy to resolve. This is working at 20 hertz, we can still resolve it. In reality, we operate this system at 200 hertz, which our eyes cannot resolve. At this scanning rate, we are able to provide a real-time imaging capability to see all the single red blood cells flow in capillary junctures here. You can see how the red blood cells bifurcate at this point, which is not entirely random. Much more importantly, we follow each red blood cell as they fly through this capillary loop by using 2 laser pulses spaced by about 20 microns. So that means we literally send 2 pulses at nearly the same spot on this single red blood cell to examine the oxygen saturation, because you need 2 colors to examine the oxygen saturation. We're watching the color change of a single red blood cell as they travel by this capillary loop, and we can monitor how oxygen is released and follow them. So that means now we're studying oxygen metabolism at the most fundamental level, namely the single red blood cell level. As I mentioned earlier, histology currently is entirely invasive. We have to cut a piece of tissue out of the human body or animal, then process it by fixing the tissue, by slicing the tissue, then staining the tissue. Then you examine under a microscope, which takes a lot of time. One important problem is tumor demarcation. In the operating room, physicians want to remove all tumors. If you don't, the tumors will grow back. The current process is to debulk the tumor, then use histology to test if the margin is clear of cancer. If not, the physician will remove more tissue. The physician often had to wait for the pathology to come back. That's a huge problem. In fact, in order to speed up the histology testing, we use a cryo form of histology which is inaccurate. Right now, we use in vivo imaging because DNA and RNA absorbs light. We can see cell nuclei very well. By processing the same slice, we can get HE staining images. We started 10 minutes later. Okay. So you can see they correlate quite well. So that means we can potentially use this tool in the operating room without staining the tissue, because we're using dye-sense contrast. We can tell the physicians where to cut the tumor in real time. Dr. Kawata showed very impressive super resolution imaging. This is a very hot area in the imaging field. Photoacoustic microscopy is capable of super resolution imaging as well. By using the third order effect, we're able to break through the optical diffraction limit to go beyond wavelength over 2 as a resolution limit. This is the diffraction limited resolution, which is about 234 nanometers. This is the super resolution. You can compare the two as shown right here. This may not be the ultimate limit in photoacoustic microscopy. We're still pushing this forward. Here's a quick discussion summary. In the past decade or so, this technology has come a long way. By no means are we done with this technology. We still face a lot of challenges. For example, ultrasound reflection by gas cavities and bones, aberration by adult skulls, ultrasound attenuation by the lung parenchyma. Can we deliver light at even a greater depth? Ballistic imaging allows you to penetrate 1 millimeter. Photoacoustic tomography allows you to penetrate 7 centimeters, maybe potentially up to 10 centimeters. If we can overcome scattering, absorption becomes the only factor that limits your penetration. But the 1/E absorption decay constant is up to about 10 centimeters. 10 times that number gives you 1 meter. Can we one day penetrate tissue using visible or near infrared light up to about 1 meter? If we can do that, we can use near infrared light or even the red light to go through the entire body to provide whole body human imaging. This is a great dream to have, but nobody can do that yet. Toward those great dreams, we've demonstrated some initial data. Can we image human brain using this technology? This is a CT image of the skull. This is a photograph of the skull. We actually use a back brain here to mimic the human brain in this ex vivo case. Can you predict if we can see anything by going through a thick adult human skull? Very encouragingly, we see the gyri in this brain. One day, if we can image this in vivo, we can potentially provide functional imaging using this device as a complementary tool to functional MRI, because we can image functional contrasts more directly, and we can image in real time. We can potentially provide a much more helpful tool. We're also working toward overcoming the scattering problem using a technology called time reverse, ultrasound encoded optical focusing or true focusing. In astronomy, we use a guide star to correct for an aberration due to the atmosphere. In biological tissue, we don't have a guide star. We artificially created one using focused ultrasound beam. This beam is going to shift, color shift, the coherent laser light. Outside the tissue, we record the frequency shifted light. Then when we time reverse that component back into the tissue, as a result, light can be focused back into a highly scattered medium. So this may be the first step toward penetrating up to about 1 meter in biological tissue. Obviously, this is still very early. Here's a quick summary. Photoacoustic tomography is based on light excitation and ultrasonic detection. Optical diffusion limit has been broken. We penetrate 7 centimeters one way. That means if you penetrate from both sides, you penetrate about 14 centimeters, which can be used, which is very useful in biological imaging or biomedical imaging already. Single capillary, single cells, and even single organelles can be resolved in vivo. We've demonstrated down to about 90 nanometer in resolution, which is super resolution already. Multi-scale imaging is capable, it is possible. The sensitivity to optical absorption is extremely high. It's actually at 100%. Any molecules can potentially be imaged, either non-fluorescent or fluorescent. This is very different from fluorescence imaging. Multiple chromophores can be resolved. Functional imaging comes from endogenous contrast. Molecular imaging comes from targeted contrast. Reporter genes even can be imaged. Doppler imaging of flow has been shown. Data acquisition is fast. There are no speckle artifacts, very different from ultrasound imaging or OCT imaging. We use non-ionizing radiation only. The systems are relatively low cost. I need to give credit to my lab members. The red names are the major contributors to this talk. Thank you very much for your attention.